Okay. Satish, shall we start? It's 7.
Sure. Yes. Please. Yes, please.
Okay, Satish. Right. We'll. Yeah.
Thank
Yeah.
you. Nice talking.
So,
Thank you.
good evening, all. On behalf of Department of Astronomy, I welcome you all. I welcome you all for today's lecture by Dr. V.H. Satish Kumar. And we welcome you, Dr. Satish, and thank you for accepting this for this lecture today. But before you begin, please allow me to introduce you to our audience. Dr. Satish has done his Bachelor's of Science from University of Mysore, Master's in Science in Astronomy from Osmania University. He has done MPhil from University of Hyderabad and PhD in Theoretical Physics from Baylor University, Texas, US. And his work was on black holes and quantum gravity. And at Baylor, he taught astronomy and physics to over 2,300 students. That's astonishing. And was nominated 4 times as the outstanding instructor. In 2015, his PhD thesis got the Outstanding Dissertation Award among all the departments of science, engineering, mathematics at Baylor. In fact, in 2013, he got honorable mention in the International Gravity Research Foundation essay competition. And later he did 4 years of postdoctoral research at Rio de Janeiro State University and a short stint at the National Observatory. And since 2019, he has been as an assistant professor of physics at the Federal University of State of Rio de Janeiro in Brazil. It's wonderful to have you here with us, Dr. Satish. And now, without any delay, I would request you to please present your lecture. Thank you very much.
Thank you so much. Thank you so much. I'm very happy to be here. Okay, so today I will make a case why physics is fundamental, right? Usually when I give a talk, I usually talk about something I recently published, right? So my recently published articles here, I found some solutions, some exact solutions in a theory of gravity called Einstein ether theory that was published in September this year. And the other one is about the existence of new singularities in Einstein ether theory, another theory of gravitation. Here I used the same ideas as Roger Penrose, who got Nobel Prize this year, and Stephen Hawking, to prove that there are new singularities in this theory of gravity, right? And there's another one which I haven't published yet, naked singularities in Einstein ether theory, right? But I thought of giving talk about these things, but these are very complicated things, highly mathematical and far removed from observation and other things. So it would be dry if I gave talk on this. So instead, I made the other extreme choice, that I chose to talk about something more general. Usually, like you may have other speakers who will talk about gravitational waves, black holes, and other things, right? So although I work on extensively on black holes and quantum gravity, but today I want to give you a bigger picture, a grand view of all areas, and then make a case why physics is more fundamental than other sciences, right? There was this C.P. Snow, I think in the 40s, right? He gave a very famous lecture called The Two Cultures. So he basically said, in our intellectual pursuits, there are 2 types of cultures. One of sciences, the other of humanities, right? You can basically divide people by asking this question, right? So if you are at a party, you can ask this question, hey, do you know what second law of thermodynamics is, right? If the person says yes, that means he's a science person. And ask, hey, have you read a play of Shakespeare? If yes, then this person is humanities person, right? Arts and science, right? So you can say arts and science, arts person and science person. But sometimes there could be people who know both, right? So he said, but you can see that fraction is small. The people who know both second law of thermodynamics and play of Shakespeare is a minority, right? So majority of the people live in either that category or this category. And he says this is a disadvantage in solving problems, world's problems, either in arts or sciences, right? So I go a step deeper, right? Um, let's do a. I usually want to interact with the audience a lot, right? So maybe okay. So how do we do this, right? I will show you some pictures. Just for a second, you have to guess how many objects you see in the picture, and then maybe enter in the chat, right? So make it very quick. Be ready, right? So I show a picture for just a second. You have to guess how many objects are there and enter the number in the chat, okay? Beautiful. Satya, Vivek Reddy is 5, Satya is 4, right? So very good. 5 is the correct answer, right? So I go back. So now, fantastic, right? So now let me show another one and then guess the number of objects. Many, right? That's a good answer. 1 to 13 is a good answer, right? So about 20. Okay, sure, right? So let's do one more. How many trees, coconut trees, do you see? Somebody said like 60, like they're so sure. Finite number, very good. So you're a mathematician, Aman. So less than 30 is a good answer too. That's a physicist answer. Okay. Basically, if we have objects 5 or less, we can just look at them and then tell how many are there. This is called subitizing, right? So subitizing is just telling the number of objects without ever counting, right? And apparently we are limited by this capacity. So as we saw in the picture, right? So 5, everybody was clear, but with more than 5, like some people can tell up to 15, 20, right? So, but that's not normal. So what's the moral of the story? If you want to count the number of objects, right? So more than 5, you have to learn counting, right? You cannot just say and then see, oh, there are few here and more there, right? And this becomes worse. For example, if there is 1 billion and then there are 1 trillion, we don't know what it means. So we basically do not have emotions for bigger numbers. Apparently that starts decaying after about 5, right? This is called subitizing, right? So now, oh, okay. So I wanted to play a music. Oh, I did not prepare that music, right? Music, and then I wanted to ask you the question. Hey, do you like this music? Right? Usually, I don't think anybody is going to say, "Oh, I can't tolerate this." No, like you can still appreciate the music even if it is. I think it's going to cause some. Just a second. Okay, I think the relay is worse, so I'm going to avoid the temptation, right? So basically, I was about to play Portuguese music, right, which you've never heard, and I think you would appreciate that. So there is a fundamental difference in our ability to enjoy music and arts, and in our ability to appreciate numbers and equations, right? Nobody goes home at the end of the day and then solve a theorem in mathematics and then relax. No, you watch Netflix, you watch drama, you watch, you need relaxation, right? So there is fundamental difference, not in our thinking, right? It's hardwired into our our abilities that we perceive arts and science differently. So if you have a problem with physics, with astronomy, with sciences, with mathematics, it's okay. That's natural, right? You don't have to worry about that. So let's go one step deeper, right? So everything that you can study in the university can be categorized into four, right? One is humanities. I write this like human sciences. I think that sounds better than humanities, right? So in Portuguese, it's Ciências Humanas. That means human sciences, right? So everything has sciences in it because it's a systematic study, right? So we have human sciences, social sciences, natural sciences, and mathematical sciences, right? So in human sciences, what do? We study the human condition in a social, cultural, and personal context, right? So examples are languages. If you study Telugu literature, that's human science, like philosophy, religion, right? Visual arts, performing arts, history, all these are about humans, right? If there are no humans, there is no meaning for any of this, right? And then we have social sciences. Here, it's not about individual human, right? It's about the collective thing. It's about the society. So you study economics, sociology, psychology, right? So psychology can be human sciences too. So there is a very fine difference between what is human science and what is social science, right? Geography, political science, law, anthropology. If there are no human beings, what do you do with any of the IPC sections, right? So anthropology is the study of humans, right? So this is what we do in human sciences and social sciences. They're almost, you can call them arts, right? That's what we call. And natural sciences. Here we study the nature based on empirical evidence, right? We observe something and make a theory and then make predictions and verify the observations and then keep those things, right? So if it's not, we throw away or improve our theory, right? That's how science works. So physics, chemistry, biology, astronomy, geology, right? So these are the natural sciences. And then there is mathematics, right? So in mathematics, you kind of make the rules, right? So you play by the rules. Just like a cricket, just a game of cricket, just like football. There are rules and you play by the rules, right? You can make the rules. Those rules can be found in nature, but it's somehow independent of anything else, right? So once you make a proof in mathematics, it's forever. So once you have proved Pythagoras theorem, after 200 years, nobody says, oh, somebody disproved a theory of Pythagoras. No, right? Because it's clearly said in a plane, and this is the thing, right? So it has all these things. So mathematics has some level of timelessness, right? So some level of independence from everything else, from nature. Whereas natural sciences, yes, you can disprove theories and then throw away those theories, right? So what I'm saying is humanities and social sciences, right? So human sciences and social sciences are about human beings and societies. And they say so many things about our human nature, right? But they don't help us in understanding the nature. Of course, we are part of the nature, right? But the other part of the nature, for example, there is no poem in any languages that can tell when is the next solar eclipse going to happen, right? There is nothing in, there is no law in sociology or anthropology that can tell how long it takes for an object to fall to the ground, right? So all these things, no, right? But so they have different abilities, right? So they tell us about ourselves, our identities, and our place in nature and other things. So they are definitely important, but they do not help us answer other questions about nature, right? Similarly, can physics tell something about evolution? Oh, okay. So that's a different story. So let's go, right? as I already said, mathematics is independent of nature, right? So um, the discoveries in mathematics are born out of pure logic, right? So and other strange thing is, in fact, Wigner many years ago he wrote an essay, gave a lecture called "Unreasonable Effectiveness of Mathematics in Physical Sciences," right? So we do not know any theory which has predictive power, right? For example, Kepler's laws that you study in celestial mechanics, right? Um, or the theory, the spectroscopy, right? So the laws of spectrum, where you can use the tools of spectroscopy to tell how many elements are there. All these things are based on, for example, spectroscopy is based on quantum mechanics. The laws of quantum mechanics are written in the language of mathematics, right? So we do not know any other language. There is no other way of expressing the laws of nature other than mathematics, right? So these are the three inferences I made so far, right? So the first is we have different abilities for arts and sciences. Second thing is arts are very important. I cannot stress this enough, right? So important for us as humans, but they are almost useless to understand nature, right? Mathematics has a different thing, right? So it's independent of any of these things. Okay. So basically what I did was, like, I told you what are the areas of knowledge, and basically I discarded already human sciences and social sciences, as they're not going to answer the fundamental questions about us, right, about nature. So they're not useful. Mathematics is good, but it's somewhat independent of any of us. Mathematics can exist without human beings, right? In nature, there are so many patterns which we found by artificially playing the games in mathematics, but they exist in nature, right? So it has this supernatural power, supernatural element to it. So let's keep the mathematics aside. So now we are just left with natural sciences, right? So the first science is biology, right? So biology is the study of living entities, right? One can say all the problems, like everything in social sciences and human sciences, are problems in biology, right? In fact, using evolutionary biology, neurosciences, and other things, you can explain lots of things that are big questions in social sciences and humanities, right? In psychology, right? Why human beings don't like social distancing, right? So why don't they want to stay at home forever, right? Why do they want to socialize? Why do they want to do certain things? Why they do, right? This will describe in poetries, in paintings, in plays and everything. But the fundamental reason comes from evolutionary biology, right? So you can say biology takes care of everything, right? So it takes care of social sciences and human sciences. But the problem is the life itself cannot exist under arbitrary conditions, right? So only, for example, 1 Kelvin degree 1 Kelvin, right? 1 Kelvin is how many degrees Celsius? Can somebody quickly answer? Right? 1 Kelvin is not like 1 degree Celsius. Beautiful. Oh, I think Sriram is answering. So now, it's so low, right? So if you stay in the refrigerator, which is perhaps like -5 or 10 degrees, I'm not sure, for more than certain number of hours, you will die of hypothermia, right? In the same sense, you cannot stay in the hot sun forever. Of course, Hyderabad is very hot. Rio de Janeiro is also very hot. But it's hot only temporarily, right? So we don't stay in the sun. People do die under very hot conditions. So, but do you know what animal, right? So what living entity has the highest resilience? For example, this picture I am showed here, right? These are called water bears, right? So the name is very good, tardigrade. Yes, perfect, right? So they are the ones you can send them to space. They have in fact sent them to space. They can survive under extreme conditions, right? So I am being very generous. I would say life can exist anywhere from 1 Kelvin to 1000 Kelvin, right? So beyond that, life doesn't exist, right? So everything that we study in biology, right? All the evolutionary theories, the cell theory, the genetics, and everything, um, that's helpful only in this temperature range. For example, if you have a system, you cannot use evolutionary biology to explain the sunspots, right? Uh, that's not possible, right? So although biology is very important for us, right? So for example, now we are getting vaccinations, right? For coronavirus from research in biology. But medicine is just an applied biology, right? Um, that's very essential. But again, it doesn't give us a deeper, it doesn't answer some of the deeper questions in nature, right? So next comes, so I discarded biology also as a candidate to explain the deepest questions about nature, right? Um, so now comes geology. Geology is the science of the earth, right? As you all very well know from your courses, right? So earth it has a finite amount of lifetime, right? This has been around only for about 4.5 billion years. So all the theories of plate tectonics and other things, they are not so useful beyond Earth. But you might say, for example, there are moon quakes, right? So you can understand it's not the geology, it's the, okay, lunology, maybe you can say, right? So the geology, for example, geology with a small g of the structure of the moon and other things. You can understand from your knowledge of the Earth, because Earth is a planet, right? So you can study other planets based on this knowledge. So geology is very important. Um, but it's important. It helps us in understanding the planets, right? So Earth and other planets. So we are already slowly going into astronomy now. But the planets can be formed only below 10,000 Kelvin. If the temperature is higher than that, the molecule, yeah, sure, hydrogen cloud or the molecules, whatever you call the dust from which the supernova yeah, some debris thrown from supernova, all these things, right? If those things have more than 10,000 Kelvin, you cannot form a planet, because the pressure, right, the movement of these things would be higher than the gravitational power, right? So you cannot do this. So our knowledge of geology, right, we can extend that to study other planets, is very important, right? So since you are studying astronomy, these days exoplanets is a great area of research, right? So far we have found, I think later I have, oh, there you go. So look here, so far as of today, as of this morning here, right? So 4,391 planets have been found. Let's say 4,400. Let's say 4,000, right? 4,000 planets, right? Just 20 years ago, we didn't know many. 30 years ago, you can say zero, right? So now we know more than 4,000 planets, right? Um, and the hot area of research in exoplanet is we are looking for sun-like stars with Earth-like planets, right? So in this study, right, so basically we are looking for something called a Goldilocks zone, right? So habitable zone, right? So maybe can we go there, colonize those things, right? This is the question. This is the interesting question we are looking for, right? So this is a question in astronomy, right? This is all done by, for example, Kepler satellite is a famous thing that found maybe 80% of these planets here, right? But in your search, you have to have a very firm knowledge of biology and geology and other things, right? It's not just astronomy to study these things. But again, these theories, which make up all these things, like planetary sciences, right, are again good only till 10,000 Kelvin. So you cannot use this knowledge to study, for example, the sun, right, or anything else like galaxies, right, the formation of black holes. No, it's not possible, right? So then come chemistry, right? So I already discarded humanities, social sciences, mathematics I've set aside, right? So you cannot discard. And biology was the first one to go, then geology, right? So then came chemistry, right? So chemistry is applicable to molecules and atoms, right? So chemistry happens outside the nucleus in an atom, right? With the electron exchange of the electrons and other things. If you have temperature more than, let's say, 10 trillion, right? That's a lot of temperature, right? So the sun has the core of the sun has only a few million degrees. This is 10 trillion. You cannot have atoms because this temperature, atoms are the electrons are ripped apart from the atom. So you are just left with a soup of electrons, protons, neutrons, and other things, right? Or even the quark, gluon, plasma. So chemistry makes sense only for temperatures less than 10 to the 13 Kelvin, right? So anything you have studied in chemistry, all the laws of chemistry are no good beyond this temperature, right? So there you go, right? So we are just now left with astronomy and physics, right? So astronomy has objects like about 1 billion Kelvin, right? Sun is only 1 million Kelvin, right? So the billion Kelvin is a lot of temperature. Billion Kelvin was the temperature when the universe was just 100 seconds old. Imagine, right? So the universe was born and just 100 seconds old. That's how many minutes is that, right? So just let's say 2 minutes, right? The temperature was 1 billion Kelvin. So at that temperature, so here I have a graphic, right? So look here, I think it's too small to see. First stars and planets, they were formed after about 300 million years, 300 million years after the Big Bang, right? So after the birth of the universe. But we have a very good observational data. So that means we do not have astronomical objects. Astronomy, right? Astro means, for example, in Portuguese, astro means any object in the sky. Astronomy is the study of objects in the sky. There wouldn't be any objects in the sky at this temperature if the entire universe has this temperature, right? But for example, we know the picture of the universe to very high precision and great accuracy, the picture of the universe when it was only 380,000 years old. 380,000 is a small amount of time in the course of the universe, which is 13.7 billion years, right? 380 is very small. So this observation comes from, for example, started with COBE, right? So Penzias Wilson, they were the first one to recognize this, detect this accidentally. Then COBE made the decision, made the better detection. And then we have WMAP, and then most recent was something called Planck, the European Space Agency. All this comes from the tools of astronomy, right? So although there are no astronomical objects, meaning there are no stars or planets or galaxies, when the universe was that old, but the observation and all these things, tools, come from astronomy. Of course, all these things will have to go through interstellar medium and other things. So astronomy, although that, speaking of temperatures, valid only after 300 million years after the Big Bang, but it's very essential to understand almost universe from the very beginning, right? So that way, astronomy is relevant ever, like forever, since the beginning to now, right? So it's hard to discard. But the astronomy is only giving us the observational evidences, right? But the laws of like why, for example, this is called CMB, cosmic microwave background, right? So that's the, for example, when you had those old television sets or even the radio, the hiss you hear, right, is coming from that cosmic rays. Although astronomy makes precise measurements and gives this, the explanation, right? So why this is the case, we need to use physics. So that way, physics and astronomy go hand in hand But again, the fundamental explanation comes from physics, right? So here I made a kind of spiral, right? So you can see it's handwritten. And I gave this talk to high energy physicists, particle physicists, those who study quantum field theory and other things. So I changed the notation from the kelvins to electron volts. But basically you can see, right? So life, like the green part here, right? So it's a very narrow range of possibilities. That's where all the biology lives. That's where all the humanities and social sciences and everything. But you can see the biology is green, right? So yellow thing is chemistry. Look at that. Chemistry goes all the way there. And physics goes all the way to 10 to the 16 GeV, right? So that's the temperature during the inflation. That was the phase, that was the epoch in the universe when it was just 10 to the minus 32 seconds. That's a very small number. We do not have any feelings. 0.32 zeros 1 second, right? So that's too small. And the temperature was something like 10 to the 29 Kelvin. Again, you have no idea how big that number is, right? And the laws of physics, there is no reason to doubt. Of course, observationally, we can go only, for example, to 10 to the minus 12 seconds, right? Remember, it's 10 to the minus 12 second, a trillionth of a second, right? So we can create this environment in the laboratory, in LHC, Large Hadron Collider, in CERN, Switzerland, right? So when they collide protons, it creates the soup, the quark gluon plasma. Basically, you are creating the universe, the conditions of the universe, when it was only a trillionth of a second. Trillionth of a second is too small, right? So that's how, and all our laws of physics are valid. There is no question to doubt them, right? But we can but this is where it ends, right? So, but the laws of physics can go even further, right? There is no reason to doubt. So only places we do not know. We can explain inflation with fairly great accuracy with our existing theories, but there is no observational evidence so far. There was some, but it turned out to be not correct. I met those people in Princeton. There was so much of I think instead of hype, I can say excitement, right? So there is this guy called Matthias Zaldariaga. He's at the Institute for Advanced Studies, Princeton. So I was at the lunch table, and he was telling the story that he's from Argentina. His mother saw the video of this announcement, and she was telling him, "Do you know anything about this?" He's one of the world's leading experts on these things. So anyway, so the viral video made much more news than any other things. But that turned out to be false. Otherwise, those guys would have got Nobel Prize by now. Anyway, so we have a laws of physics valid until then, but that's not the end of the story, right? So the temperature goes up, and this is not 0 seconds, because there is still difference between 0 and 0.000032 zeros and 1, right? So we do not know. So this is how much we know about the universe, right? So accurately, so well. This is explained by these 4 theories. One is general relativity, proposed by Einstein, right? So he was the one who formulated. Then we have something called quantum electrodynamics by Schwinger, Tomonaga, and Feynman. And then we have something called electroweak theory, right? So we need electroweak theory to explain, for example, the fusion and other things, how the sun is giving light, right? That theory was nailed by Glashow, Weinberg, Salam. All of them got Nobel Prize, right? So 1973, Gross, Wilczek, and Politzer. So I've met Weinberg many times because he's from Texas. I studied in Texas. Wilczek, yes, I think once. Gross, yes, I've in string conferences. Politzer, I saw his office in Caltech. He has some. It's not guitar. I forgot its name. And apparently he teaches the physics of these musical instruments. That's what he does now. Okay, so sure. Okay, so these are the 4 fundamental theories, right? I'm giving them like apples and oranges because they're again different in nature. These are all quantum theories. The ones in orange, one in apple is that represents gravity, right? So that's a classical theory. This is the problem, and this is what I did for PhD, right? So how do we understand these things in the same language? How do we translate gravity in terms of to quantum theory, right? It's an open problem. Nobody knows the answer, right? So, but physics at least can go all the way up there, right? So here I created one timeline, again in terms of kelvins and electron volts temperature. You can see, again, it's just a summary of what I said so far. So biology, look at this, it's only applicable here, whereas chemistry can go all the way, right? So physics can go all the way up to here. It can explain so many range of things, right? So, and then this much of this is experimentally verified. So beyond this, we have theories and we believe that's true, but we haven't had experimental confirmation yet on those things, right? Very good. So what's the moral of the story? So nature can be studied in layers, like the layers of onion, right? So it all depends on like how deep you want to go, right? Sometimes to solve the problem of one layer, you don't have to know anything below or anything above. For example, take the example of biology, right? So to understand evolution, you don't have to know the psychology of human beings. You don't have to know sociology. You don't have to know the one layer above, right? So one layer below in the same thing. You do not have to know chemistry, for example. But knowing chemistry is molecular biology that helps you explain so many unsolved questions in evolutionary biology. But you can happily do that without knowing one, right? So this is so I'm putting it in very general terms, but there is a theory called renormalization theory and effective field theories and other things, championed by someone called Ken Wilson. He got Nobel Prize for his work. Basically, in physics too, again, we can make theories which are valid only in short intervals and make predictions and be happy with that. They're not fundamental theories. They're called effective theories because they can explain only narrow range of phenomena. For example, Newton's laws of gravity and Newton's law of gravity and laws of motion, they're effective theories. You cannot use Newton's law of gravity to explain black holes or the birth of the universe. We use general relativity of Einstein, right? So that's a bigger theory in its range than Newton's gravity is, right? But they're good enough for many purposes, right? So we send satellites using these things. Okay, so what's the other inference, right? So there are many layers, but the deepest layer can only be studied in physics using the laws of physics, right? So that's why we call this fundamental, right? But again, just because it's fundamental doesn't mean it answers all the questions, right? We cannot use the laws of gravity to explain why so many people are stupid, right? No, we cannot do that. In fact, this question was raised by Schrodinger in 1944. I have the book right here. I never paid attention to this kind of things. So now I have 4 undergraduate students. They are biology majors. I cannot do my kind of research with them, but instead I do what they are interested. Basically, the origin of life, right? So how do we go from molecules to living things to a cell, right? What is the transition? Like how can, for example, there is no living thing with only 10 molecules, right? When do molecules become living entity, right? This transition, we don't know. We know a lot of physics, but so far we are not able to explain how do we go from molecules to cells, right? The origin from non-living to living transition of matter. How does matter become living thing, right? So fundamental doesn't mean it answers everything, right? So we should be careful in disregarding other things. So I'm not saying physics is the ultimate, everybody should study physics. No. Depending on what you want to answer, right? So you have to know, right? So whereas I'm saying most fundamental of nature, right? Same thing. Philip Anderson is a very celebrated condensed matter theorist. He is a Nobel laureate as well. He wrote a famous essay. He did so many things. He made half the discoveries in condensed matter physics, what we call solid state physics, right? But he's very famous for his essay, some 3-page essay called "More is Different" or Emergence. Basically, every new layer of physics brings up new phenomena that you wouldn't know that when you are at the layer below, right? So this is called emergence. For example, if you have just one molecule, there's no elasticity, there's no viscosity, right? So all these kind of things, viscosity, surface tension, elasticity, these things come into being only when there are more of them, right? So that's why he said more is different. Same thing, with one atom, one molecule, we do not have life. So with more of them, we have life, we have cells, right? So how does this emergence happens, right? So basically he's saying each layer of knowledge has its own thing, and everything is equally fundamental, right? So knowing how molecules become living entities is as fundamental as knowing the birth of the universe. So that's what basically he says, right? So I am at the end. The other plan I had for talk today was to kind of talk about all the Nobel Prizes in gravitation, astronomy, astrophysics, and cosmology, right? But again, you'll find lots of people who talk about these things, so that's why I chose to talk about this. Just let's go through this list quickly, right? So in 1967, that was the first Nobel Prize given to anything related to astronomy, right? That went to Hans Bethe. Hans Bethe was at Cornell. This is for his theory about the why the sun shines, right? So the nuclear reactions and other things in the sun. It's not because of a coal is burning, there's a wood burning, so using nuclear reactions, right? So that's Hans Bethe. Then in 1978, as I mentioned, the glow from the early universe, right, was discovered accidentally by Penzias and Wilson. They got the Nobel Prize in 78, right? 83, our own Chandrasekhar and Fowler got Nobel Prize for explaining white dwarfs, right? So structure of stars and other things. And we do use Chandrasekhar's stellar structure textbook at Osmania for the stellar structure course, right? So then in 2006, John Mather and George Smoot, I've met John Mather. Again, them for COBE, the Cosmic Microwave Background Explorer, right? So they basically made the measurement of Penzias and Wilson a more refined measurement. And then they showed that this follows a block body curve, right? So Perlmutter, Brian Schmidt, and Adam Rees, in 2011, they got Nobel Prize for discovering that the universe is accelerating. The discovery they made in 1998, right? So the most recent is Wes, Barry Barish, and Kip Thorne in 2017 for the discovery of gravitational waves, right? I've been to the house of Kip Thorne. Then 2019, Jim Peebles, Michael Mayer, and then Kalos. For Jim Peebles for cosmology and Mayer and Kalos for exoplanets, right? And this year, Nobel Prize went to Roger Penrose. I've been using his ideas in my own research all my professional life. He's basically a mathematician, but a great physicist as well. And Genzel and Gaze for their measurements of the planetary orbits around the black hole, supermassive black hole in the center of the galaxy, right? That's this year. So if you see the thing, like before 1967, there was zero, right? So Nobel Prize started in 1901. For nearly 70 years, there were no Nobel Prizes for astronomy or related areas because they were in the primitive stage, firstly. Secondly, they were not considered like physics, right? So they thought it's different. So one of the purpose for me to give this talk is to eliminate that barrier between the subjects. So what is physics, what is mathematics, what is chemistry, what is this thing? No, these are very arbitrary. Nature doesn't care what subject it is, right? So we have made this for our own convenience to teach in the university, right? So young people, so don't be bogged down by these labels, right? So if you have a problem, okay, you want to understand the cellular structure, go wherever it takes. You may have to learn physics, you have to learn simulations, maybe computer science, right? So many other things, right? So don't be bogged down by the labels, right? Oh, I am in astronomy, so I don't study physics. No, I don't need biology. No, you need biology to do so many other things, right? So study whatever is required to solve your problem, right? And do not discard any of the subjects as inferior or superior, anything. No, right? So if you come out of that mindset, I think you can do wonders, right? So apparently the Nobel Prize Committee came out of that mindset only in the 60s, right? So now look at that, almost every year, right? So 2011, 17, 19, 20, right? So it's too much astronomy. It's raining astronomy, right? So it's good time for you to learn about things and then start doing physics and astronomy, right? So that's all I have to say. Thank you so much for your attention, and Happy New Year 2021.
Thank you, Dr. Satish. It was wonderful. You have put in a wonderful way hardcore physics into an understandable way, and of course, the inquiry into the universe should be continued because that's what we are. We are a part of it. That's what we are. Now, I request the participants to put their questions, precise questions, in the chat box as well. If with the permission of the speaker, you can as well unmute your mic and then speak out your questions, please.
Sure. Yes. Ask me any question. Don't be shy.
Yeah, there's a one question in the chat box right now, Dr. Satish.
Okay, let me take a look. You mentioned, oh my God, particle in your slides. Oh, look at that. Who is that? Akanksha. Okay. What do you think this cause or source of this ultra high energy cosmic ray? That's fantastic. And I did not like draw your attention to that, but you're a very keen observer, Akanksha. How much research is being done in this field? Cosmic rays, right? I don't know the answer, and nobody knows the answer, right? There is a lot of research being done, actually in South America. In Chile, there is a big observatory for cosmic rays called Pierre Auger, right? It sounds like Pierre Auger. It's a French name. It's Pierre Auger, right? That's the world's leading observatory for gamma rays on the ground. There is other Fermi satellite placed in orbit, right? So outside, that also does the observation in gamma ray window. I mean the cosmic rays, right? So cosmic ray window. There is a lot. In fact, the 19, for example, there are 40s and 50s, right? So the decades of 40s and 50s of the past century were full of cosmic rays. We learned so many things about the fundamental particles, particle physics from cosmic rays. In fact, TIFR, Tata Institute of Fundamental Research, right? So I think Sriram worked there. They were pioneers in cosmic ray research. Homi Bhabha started that. So there is a lot of cosmic ray research being done, mostly observational. Theory-wise, there are many theories saying mostly they are jets, maybe black hole explosions and this kind of things, but there is no confirmation, right? So this is my answer is as good as your guess. So Akanksha, you should do your PhD in cosmic rays. What's the next question? Aman, sir, on quantum gravity. How small do we go in terms of distance between called elements, and what spatial happens at that point? Okay. Again, quantum gravity, the biggest problem is we do not have any observational data, right? So there are many theories, two leading theories. One is string theory, right? I wrote a paper on that. It's not just quantum gravity. It unifies all the theories of all the fundamental theories, all the quantum field theories with gravity. Yes, you have written in a paper something like Planck length. Yes, yes. Planck length is the distance supposed to be where, right? So where the quantum gravity, this is the Planck length, right? So 10 to the 19 GeV is the corresponding energy, right? That's where the quantum gravity becomes relevant. For example, you don't need to know quantum gravity, anything about quantum gravity to answer questions, formation of galaxies, quasars, stars, life, nothing, right? So this is the problem. But philosophical, let's avoid the word philosophical, right? So we have these theories, right? So it's not good to have theories of nature being written in two different languages. One obey laws of quantum mechanics, which are completely different from laws of classical physics, right? So we have to have one unified picture that we know from just by knowing these things. That's the motivation. But there is no observation which begs the need for quantum gravity. And there is no observation to discriminate our theories, which is correct, which is not correct. So that's why it's shooting in the dark. It's very, you have to be very brave to go into the research in quantum gravity, because the chances of you not succeeding is almost sure, right? But anyway, we don't go to succeed. We go for the pleasure of it, right? So I myself work on quantum gravity. My PhD was on those things, right? Yes. So moral of the story is yes, Planck length is where it comes to, and there are a few theories, right? But none of them, we don't know which one is correct, which one is not correct. And there are factions of physicists, right? So just like politicians, like some don't like the other, some don't like this is because physics is done by human beings, right? But again, I recommend you to go study quantum gravity, right? To study quantum gravity, we need at least these four things, right? So you need to know all the quantum field theories and particle physics and general relativity and cosmology, right? Then maybe you need to know a lot of mathematics. It's an adventure, right? So we do this for the adventure. Thank you for the question, Aman.
Yeah, we have.
How far has graviton discovered? Yeah, okay. No, graviton has not been discovered. If we discover graviton, that would be an evidence for quantum gravity. We have discovered only the gravitational waves, right? So we have discovered like electromagnetic waves, but not the photon of gravity, right? Okay.
Ajay Vijay, you are unmuted. You have any question? Please mute if you otherwise.
Small domain. You mentioned theories applicable to small domain with results are also good, but most of the people prefer unifying everything. Please elaborate on it. Yes, we have theories. For example, quantum electrodynamics is so good. Like if you make a theoretical calculation, right? Just stay in your room. Don't even look out of the window. Just simple calculation. Not so simple, but lots of calculations, right? Then you get a number, right? What should be, for example, the magnetic moment, anomalous magnetic moment of the electron or something, right? So you can calculate that to, for example, 9 decimal places, some 0 points, some 9 decimal places, and go do the experiment, and all of them agree with each other, right? So it's the most accurate theory that we know, and that's the theory is required for understanding matter, right? So if you want to know superconductivity and this kind of things, anything in material science, QED is helpful. But why do we need this? So we know there is something called Landau pole in quantum electrodynamics. It's the energy beyond which the quantum field theory, the quantum electrodynamics is not valid. But that's so far, you're never going to do an experiment to reach that level. But that doesn't stop some people. Some people want to make this a perfect theory as possible. It's just the personal view, right? So just to make it as perfect as possible, right? That's the reason why. But if we don't find that theory today, is it going to stop us from understanding other things? Probably not. But we found the theory. Maybe we understand the things better than better. So, yeah, that's the approach. It's a which one is important, theoretical research or observational? That's a good question, because that's a real question, right? So many people have this um, problem, philosophical dichotomy, right? So what to do, right? I wrote a few papers on phenomenology, right? So that is something like between observation and experiment, between theory and observation, theory and experiment, right? So I kind of thought that doing phenomenology, which is like observational, is somewhat inferior, right? So doing theoretical research is more awesome, right? Glamorous, because Newton did, Einstein did, Hawking did, right? But these are just false, let's say, ideals, right? It's just your skill set, right? So observation is as good as theory. Observation is as relevant as theory, maybe more relevant than theory, because with one observation you can kill 100 theories. For example, that Planck satellite I told, right? After that, there was something called BICEP. That's an observational thing. So basically, they observe the early universe, right? It's observational astronomy. Early universe. They have a satellite. They have an observatory in the in the in the South Pole, right? They observe like if there is something called B mode, right? So in the thing, forget about the details, right? So this is yeah, something B mode is something which behaves like magnetic field, right? So but B mode, right? So that's a definitive evidence for gravitational waves from the Big Bang, right? And with that thing, anyway, they do not have any conclusive evidence, but they can put a limit. If those exist, they have to exist at a scale below this, at energies below this, at some strength below this, something like this. Using this, they could kill hundreds of models of inflationary theory in cosmology, right? So one observation can kill a class of theories. For example, COBE, cosmic microwave background, right? So done in 1995, for which John Mather and George Smoot got Nobel Prize. Until then, there was a big debate between steady state cosmology, championed by Herman Bondi, Thomas Gold, Fred Hoyle, and our own Jayant Narlikar, right? And Big Bang Theory started from George Gamow, later carried on by many people. For example, recent Nobel Prize goes to Jim Peebles, right? They were all champions of Big Bang Theory. There was no way to know which one is correct, which one was not. So COBE practically shut up that whole debate. So they discarded one full theory, one class of theories, right? So observation is very, very important. Otherwise, if you, for example, what I was telling about quantum gravity, it's a purely theoretical research. Since we do not have any observation, it's easy to fool yourself, right? So that way, observation is very, very important, right? But if you don't want to do the computer programming, do the graphs and other things, but rather you want to do calculations, please go and do theory, right? Like I do. There is nothing better, nothing inferior, nothing superior about these things. It's just a matter of taste. Whatever you want to do it, right? So do it with more dedication, do it with love, and enjoy that, right? So that's all it matters, right? After 300 years, nothing is going to matter, right? So after 10,000 years, nobody knows that we were here, right? So don't worry about what is good or what's not. It's just all in our perception, right? So, but that's a very good question, right? We shall keep recording the talk. Okay, social members can go through once again. Okay, sure, yes. How many dimensions is it possible? If possible, there would be. Okay, that's a good question, Aman, right? there are theories, for example, string theory, right? So has many dimensions. The superstring theories have 11 dimensions, and this one there are 10 dimensions, and M theory has 11 dimensions, and bosonic string theory has 26 dimensions, right? There were other class of theories called large extra dimensions. I worked on that. I met Nima Arkani Ahmed, and he proposed in 1998, right? So in fact, my MPhil, I wrote my thesis on these things. We used the supernova cooling rate to put the limit on these things. So we basically concluded there can be only maximum of, I think, 7 spatial dimensions, right? I mean, yeah, 7 space-time dimensions. So 6 space and then 1 time. So we already have 3, then maybe 3 more, right? Again, these are not, it's just the limit, right? If it, using supernova data for that particular model, right? But if you change the model and go for other things, this number would change, right? So, but for all intents and purposes, so far, there is no evidence that extra dimensions of space exist, right? Yes, any other questions, please? Ask me anything.
Dr. Satish, with your permission, I hope we can provide your email ID to our participants as well.
Sure, okay. So
they can have further communications with you to
sure. Yes,
extract as much knowledge from you as possible.
Sure, thank you so much. I'd be happy to help you all. And then, like, asking question is good, right? So yes. I give the answer. Go cross-verify those answers, right? So maybe
there's
do a small project.
There's one last question, I suppose. We are very much eager to know about your research.
What next? Oh, these days, I did black hole thermodynamics for some time, but these days, okay, so you know, like Brownian movement, right? So Brownian movement is like this pollen grains with the atoms. You don't see the atoms, right? In fact, the first evidence that atoms exist came only in 1905, just 115 years ago. Einstein explained the Brownian motion, putting the debate that, okay, atoms exist, they're real. You can see that in experiments of Brownian motion, right? So that's one thing. So I'm using those similar ideas. For example, in vacuum, in quantum field theory, vacuum is not nothing. There are so many fluctuations. They're called quantum fluctuations, right? It's nothing, but there are the particles, antiparticles being created and annihilated, everything. So basically, there are quantum fluctuations. So I'm trying to find, if we have a hypothetical particle in vacuum, can it diffuse? Just like it does in, can it undergo Brownian movement, right? Can it undergo diffusion in vacuum with quantum fluctuations, right? That's what I've been trying to do. One thing. Another thing is, there is something called, this is one line of research. Other line of research is, so basically I'm trying to explain the geodesic motion in gravity as a diffusion in empty space played by the quantum fluctuations, right? Other thing is, there's something called Poincare half theorem. If you have a sphere, right, like the Earth, and if there's a vector field, basically the velocity of the air in the atmosphere, right, it has to have 2 singular points. Meaning, for example, if you have a coconut, right, so coconut has hair on its top. Imagine a spherical coconut with hair everywhere. You cannot comb the coconut without leaving two those spots, right? So those oh, I forgot the name, right? So the spots, there has to be always 2. There is no matter how you comb, right? So I'm trying to use this to CMB, the cosmic microwave background, right? So it can be projected onto a sphere. So by classifying what kind of singularities, these singularities are different from what we talk about black holes and other things, right? To see if this Poincare half theorem, it comes from topology in mathematics, completely different from physics or astronomy, right? So I'm applying that to cosmology to see if this is valid for that, right? That's again completely new. I did not know this. Right? So when you get an idea, you will have to go learn so many new things and then do the things. So these are presently, and with my students, I'm also involved in some this kind of research, right? So the physics of the origin of life, which is basically non-equilibrium thermodynamics, right? So thermodynamics of living systems. So what happens to entropy in these kind of situations? These are several things. One of my master students wants to do a thesis on education, for example, like high school education, right? So everywhere. So it all depends on who I talk to, right? So if I find anything interesting, I would work on that, and I learn the prerequisite things. Can gravity be repulsive if I remove conditions of mass and curvature? Oh, that's a good question, right? I did write an article, can gravity be repulsive? For example, dark energy is a kind of repulsive gravity, right? That's because of there are something called energy conditions, right? By changing those energy conditions, by inventing new type of matter, just like in dark energy, right? You can make this repulsive, but that's because you have that kind of matter, right? But gravity by itself is not. It's always attractive, right? To our best of the knowledge. And if you remove the curvature, yes, that's what Newton's theory is. It's always attractive. But it can give you the illusion of repulsion when you are observing, for example, a black hole from a very far place, and if you send something, it should go with increasing acceleration, with increasing speed, right? So because it's approaching the source of gravity, but because of the so many technicalities of general relativity, that particle goes slower and slower and slower. Basically, you would never see, if you throw some object into the black hole and then you're watching from very far away distance, you would never see that object going and falling into the black hole, right? So that kind of gives you an illusion of repulsion, but it's only because you are observing from far. But if you jump yourself, yes, you would go fall into the black hole, right? So yeah, these are called coordinate artifacts. I did write a paper with my French colleagues, I think 2 years ago, I think with the same title, Can Gravity Be Repulsive?
So I would interfere here.
Okay.
We can, I think it's time to thank our speaker for his patience and the time, basically, for giving your time and answering all the questions patiently. Thank you, Satish, once again from the Department of Astronomy for giving your time. You're telling something, Satish. You're muted.
Oh, did I? Oh, am I good now?
Yeah, I can hear you now.
Okay. Mm-hmm.
So thank you once again. And if at all anyone has any questions or any doubts related to whatever they are posting now, once you start about cosmology, they have innumerable number of doubts. So we'll provide your email ID later to the participants, and if you are okay with it, then they'll be in contact.
Sure. They can contact me, and I will reply you when I'm free, right?
Sure. Okay, I think we should have a group picture before we wind up the session. So
this is what they do in all these online conferences, and you guys are so professional. You are into this game so much. Sure. Why not? Should I stop sharing the thing?
Yeah, sure. And I request all the participants to turn on their videos
Thank you very much, all of you. Thank you, Dr. Satish, once again.
Thank you so much. Thank you so much. My pleasure.
It was wonderful listening to you. And of course, this was a platform to encourage all our participants to interact with people who are actually working into different areas of their interest too. And those who do not have an idea about the work which you people are doing, they get an awareness and they get motivated towards learning more about it, seeking more information about it. I'm very happy that you could patiently and with lots of zeal you could interact with the participants. Hope this will be fruitful in their future communications as well. Thank you very much, Satish.
Thank you so much. Yes, there are so many small projects that you can do as an undergraduate or a master's student that can be published in decent journals, right? So that way you learn better about research and everything, right? So ask questions, do work hard, and publish things. You can do that. I can help you with that. Okay.
Yeah, definitely. No, so Shanti, shall we wind up right now?
Yeah.
Sure.
Yes, ma'am.
Yes. Thank you so much.
Thank you, Satish.
Thank you, Shanti.
Bye.
Talk to you later. Bye bye. Bye bye, Sriram. Is he still around?
Yeah, he had a medical emergency, so he left.
Sure. Okay. No problem. Thank you, Dr. Rukmini. Thank you so much. Bye bye, guys. Happy New Year. Merry Christmas.
Wish you the same. Mr. Satish. Thank you.